You're welcome to my lecture. Our topic for today is integration. Now, integration, this is the geometric illustration of the integral function y integrating from x to a of f of t dt. So another name for integration can actually be area under a curve. Now, let's look at some common integrals. When you're integrating a power function like x raised to power n, you're going to have x raised to power n plus 1 all over n plus 1 plus k. This k here is called constant of integration. If you're integrating sine x, you will have minus cos x, and if you're integrating cos x, you're going to have sine x plus the constant of the integration. Now, if you're integrating exponential function, you're going to get back exponential function, and so on and so forth. We are going to look at some examples on how to apply these things. Let's look at this. Evaluate the following: integrating the square cube root of x dx. For B, integrate from 1 to 2 of x squared plus 3x dx. While C, you have integrate 0 to 3 of 5x cubed minus 3x plus 6 dx. Now, these symbol notations here are for integration. Now, solution. In order to solve the first one, you convert the cube root into x raised to power 1 over 3. Now, when you do that and find integration using the power rule, you're now going to have 3 over 4 times the cube root of x raised to power 4 plus the constant of integration. The similar thing will happen to B. This is a polynomial you're integrating from 0 to 1. So integrating a sum is equivalent to the sum of the different integrals. So you integrate them separately, then you add, take their sum. Okay. Now, when you do this properly, you're going to have 6 whole number 5 over 6. Now, for example C, which is the last one here, we are going to integrate component by component. You see, when you integrate component by component from 0 to 3, you're going to have 443 all over 4. By the time you substitute for the values of 3, you subtract it from when you substitute 0, and you're going to have this. Now, techniques of integration. The techniques that are frequently used when seeking antiderivative of functions are A. Integration by substitution, integration by parts, and integration by partial fraction. Okay, let's take some examples here. Under integration by substitution, we're asked to find the integral of 4 minus 3x all raised to power 1 over 7 with respect to x. Now, you say let u be 4 minus 3x. So use u to represent everything inside here. So the u will now be minus 3 dx, and dx will be minus 1 over 3 du. Therefore, this integral here will actually give us minus 7 over 24 times 4 minus 3x raised to power 8 over 7 plus c. Now, let's look at integration of even powers of sine x and cosine x. The following trigonometric identities will be particularly useful for us here. Now, sine square x will be equal to 1 minus cos 2x over 2, while cosine square x will be 1 plus cos 2x over 2. Let's take this example here. So calculate the integral of sine square x dx. Using the formula for 1, you simply replace sine x squared with 1 minus cos 2x over 2. And you now separate them this way and now integrate them component by component. So it's as simple as that. And you're going to have x over 2 minus 1 over 4 sine 2x plus c. Remark here, to find the integral of a similar trigonometric function like sine 2x cos x dx, what you're going to do here is you say let u be sine x, and the u will now be cos x dx. Therefore, your dx will now be du over cos x. So this entire question here will now be integral of u squared cos x du over dx, and which will simplify into the integral of u squared du. And when you find the integral properly, you're going to have sine x raised to power 3 over 3 plus the constant of integration. The integration by parts. The formula for integration by parts is if you are asked to integrate u dv by parts, the answer is uv minus the integral of v du. How does that work? Let's take this example. Evaluate the integral. Integrating t times exponential raised to power minus 3t with respect to t. Now the solution. You state the formula for integration by parts. So we are going to take this thing carefully. Now what is your u? You let your u be t. Let your dv be now exponential raised to power minus 3t dt. Hence, du dt, which is you're differentiating this with respect to t, and you're also integrating dv in order for you to get v. So you do that, you get this properly. So the final result will be that the integral of t exponential minus 3t with respect to t is equal to minus 1 over 3 t exponential raised to power minus 3t minus 1 over 9 exponential minus 3t plus c. Now integration by partial fraction. We want to integrate a quotient. Now you're not going to integrate this in block the way it is. You're going to split it into two different fractions. That's why it's called partial fractions. Okay, and when you apply your concept of partial fraction, you're going to find your a and your b. So in this case, a is minus 1 and b is 2. And when you substitute that properly, you now take the integration and integrate component by component. Then you're going to have minus ln x plus 3 plus 2 ln x plus 4 plus constant of integration, because we know that in logarithm addition means multiplication, okay, while subtraction means division. So that is why you are now having this. Let's look at application of definite integral. The definite integral is used for solving a large varieties of applied problems like area, finding volume, finding liquid force, length of curve, work done, and some other problems in economics, biology, physics, and engineering. But let's take these few examples. Find the area of the region bounded by x axis and the graph of f of x being h squared minus 1, ranging from x. The axis is from 1 to 2. Now, this is the representation of the problem. Area equal to the integral from 1 to 2 of x squared minus 1 dx. So we're already familiar with this. When you do the integration properly, you're going to have 4 over 3. Okay. Now, when x is 1, you're going to have 0. Well, when x is 1 here, and when x is 2 in here too, you're going to have 3. So you use this information to plot the graph. You see, and this is what you're going to have. The shaded portion represent the area under discussion. Let's take a second example. A particle moves along the x-axis from x equal to 1 meter to x equal to 5 meter under the influence of a variable force f of x, given as 2x squared plus 2x Newton. Determine the work done by the force. Now, the work done by a variable force is given by this integral. W equal to integrating a to b of f of x with respect to x. So hence our W is now integral of 1 to 5 of 3x squared plus 2x dx. And when you do the proper integration and substitution, you're going to have 148. So therefore, the work done is 148 joules. And this is the graphical representation of the problem, the work done by the available forces. Thank you for listening.